Great, so we have talked about confidence intervals. We've covered that in class. We had a lot of examples. There are ones worked out on Canvas and also on GitHub if anyone's interested to look further into confidence intervals. And so that prepares us to talk about hypothesis testing. Now, I think it's very useful to try to relate the concept of confidence intervals to hypothesis testing. I think there's a very natural segue to move into hypothesis testing. So confidence intervals were very useful from the perspective of getting at the uncertainty in a sample statistic. Take a case where we drill two wells, well 1, well 2. We estimate V shale, average V shale along the well. We get 15% and 17%. Each one of them we could calculate a confidence interval. We know the sampling distribution. Perhaps we have enough samples. It should be student-y, but it could also be Gaussian if we have enough samples. We know the spread of the distribution directly from the standard error. And so we have the entire distribution. We may pick the P 2.5 percentile and the 97.5 percentiles to report as in fact, our confidence intervals. Upper and lower bounds, and we could do all that for each well independently. But at the end of the day, you might be more interested to know if in fact these wells come from the same population, or is there a change in the rock? That would impact your decision making. Are we able to use the same type of completions methods, the same type of drilling methods, or do we think that this is now new rock and it's a new world we got to learn about? And so it would be very useful to understand whether or not they could come from the same population. So we could compare the two means, and we have uncertainty in the means with the confidence intervals, and we could look at whether they overlap with each other. If in fact they don't overlap, you tend to have kind of this, they are separated significantly. Maybe then you'd say, no, they must be two different populations. That would be useful, but it's not very robust. The most would be to define a new statistic that describes the difference between the means. And if we understood the way that statistic was distributed, its standard error, we could then assign thresholds based on a confidence interval, and we could, or a probability interval there, we could assign thresholds and we could determine whether or not the means are significantly different from each other, either negative or positively relative to each other. If we did that, and we tested that given the measures that we have, whether or not we end up on the tails or within the body of the distribution, that would be a hypothesis test. That's what it's all about. So that's how it links. So basically, we're using the same concepts of standard error and scores and counting for shape, sampling distributions. The difference is now we are testing whether or not something is different than something else. So what does a hypothesis test look like? What is the anatomy of it? Well, we have the hypothesis, which is a statement about the population parameter. This is essential that everything we do with hypothesis testing is related to the population. We're using the sample data to try to say something about the population. We're not talking about the sample statistic itself. The method, we start with a null hypothesis. We will denote it as H0, and then we test it. You have to start with a decision. You start with a belief. You don't get to go in sitting on the fence going, I don't know, willy-nilly. It could be either or. You have to make a choice, and then you try to disprove it. The result is you have a null hypothesis and you have an alternative hypothesis, which are two complementary hypotheses in the hypothesis testing problem. And what does that mean? It means that once again, there's no sitting on the fence. It's either one or the other. It's either going to be the null hypothesis is correct or the alternative hypothesis. They both can't be, and there's no space in between. They're complementary of each other. The hypotheses need to be tested. You start with your null hypothesis and you test it. And so the type of test you use will depend on what statistic you're working with and the type of problem you have. So you'll use this t-test if you're comparing the means of two distributions to see if they are statistically significantly different from each other. You'll use the f-test to compare the variances of two distributions, you use the chi-square test to compare two distributions, the entire distribution, a discrete representation of the shape, and I'll show you how to do that. The result is you either reject the null hypothesis or you fail to reject the null hypothesis. So this is really interesting. The null hypothesis, you set it as your base assumption, you test it, and you can reject it. And if you reject it, you now adopt the alternative hypothesis. Or you can fail to reject the null hypothesis. The evidence supports the null hypothesis, you fail to reject it. You never prove it, you just fail to reject it, which means your null hypothesis will live to fight another day. It will stand up there and it will just continue to be tested, and it can be failed to be rejected or it can be rejected. The error types that we deal with are we have type 1 error where we incorrectly reject the null hypothesis. What is that equal to? Well, from our talk about confidence intervals, it would make sense that that would be equal to specifically the alpha value, which in many cases was 5%. We accepted the fact that the distribution could be correct and everything could be fine, and you could still have a value outside of that interval 5% of the time, and everything's still cool. That's the way it is. So in the case of hypothesis testing, our alpha level will be the probability of a type 1 error, which we have to accept and live with some type 1 error. You don't get to live with complete certainty. You don't get to live with a world where you have no error. We'd have no power to our test unless we accept the potential of some type 1 error. Type 2 error, incorrectly retaining a false null hypothesis. So that can also happen too. Okay, let's show you what the form of a hypothesis test looks like. I'll give you two examples of a hypothesis test and the way it's set up. You collect data from a new well. Does the new data come from the same population as the previous wells, or is there a geologic discontinuity? I always like to say, are you sampling new rock? It's not the same population reservoir that you were dealing with before. It's distinctly different. So you want to test if the means are the same with the new data versus the old data. The null hypothesis is that the new population mean is equal to the old population mean or the previous population mean. The alternative hypothesis is that the means are unequal to each other. Number 2 example, you have lab measurements for permeability from core data. Does the new you have a new method, for measurement. Does the new method result in a consistent amount of permeability variance? Is the permeability variance different with the new measure? So we want to test if the variances between the old measure and the new measure are the same. So the null hypothesis is that the variances are the same. The permeability variance of the two methods are the same. The alternative hypothesis is that the permeability variance of the new method is different. Okay, so that's it. So every time you're setting up one of these tests, you should have a statement and you have a null and an alternative hypothesis. You could denote the alternative hypothesis as H1. You could also do HA, but I've seen both. And that's fine either or. Okay, so now here's more discussion about the method, specifically what are the steps involved. And so what we'll do is we'll calculate a test statistic, a measure divided by the standard error. So this is very interesting. What it is your measure of difference is being standardized by standard error so that now you can compare it to a distribution, a statistic distribution that is itself standard, which remember standard just means mean of 0, standard deviation of 1. And so by dividing by standard error, you're getting your test statistic or your test value into the same distribution so that you can compare it to the standard distribution that you'd expect for that sampling problem. You then compare, then you look up the critical value from a table or a function. So The critical value is simply going to be, remember with confidence intervals, we were talking about, you were talking about the fact that the lower and upper bound would be equal to, in a two-tailed test, the p 2.5% and the p 97.5% if we have a confidence level of 95%. So the critical value is just like that. We want to look up the lower and upper bound from the standard statistic distribution given any information that's required, such as the degrees of freedom. That's it. That's what we're doing. Then we compare the test statistic that we calculated up top that was standardized by standard error. We compare it to this critical value, that threshold, upper and lower threshold. And then we find out if we're inside or we're outside that threshold, and that's how we decide to reject or fail to reject our null hypothesis. What are we doing? Graphically, there's sampling distribution for the thing that we're sampling. The difference is a mean will have its sampling distribution. We're looking up the critical values. We're calculating the specific test statistic. And if we fall in this interval that's blue, we fail to reject. If we fall outside of that, we reject the null hypothesis, and we now adopt the alternative hypothesis as our hypothesis. Okay. Now, there's a little bit of complexity, and that's because sometimes you can have one-tail or a two-tail test. Now, it makes sense for many problems. I'll start down here. You're concerned about whether two means are the same. You don't care which one's higher than the other. And so the null hypothesis is the means are equal, and the alternative hypothesis is the means are different. Would it make sense to you that in that case you have a two-tail test? If your test statistic is mu1 minus mu2, you don't care if mu1 is greater than mu2, in which case you would have a positive, negative value. No, positive value. You don't care if it's the other way around, you end up with a negative value. You don't care which one's bigger. So you are testing, so if you have a alpha of 5%, you would divide it between the two tails and say, I can accept a type 1 error 5% of the time, but I'm going to divide that between the two tails. Because the symmetry of the problem, I don't care which is bigger. You could also set up your hypothesis, your null hypothesis, to be mu1, the population mean of 1 is less than or equal to mu2. And if you do that, what's very interesting is you're only concerned with one of the tails. Your alternative hypothesis is mu1 is greater than mu2. So we're going to reject only if we're in this 5% area up here. I don't care if it's the other way around. I don't care, in fact, if mu2 is much larger than mu1. That's totally fine to me. I don't care if I end up way up here on the tail. It doesn't matter. I'm only rejecting this, so that would be a one-tail test. Some tests, like the F test for variances, are configured so that they're one-tail by design, and that's a no-brainer. So in general, when we work on problems, we'll work with two-tail, except for in the case of the F test for difference in variances, where it's set up to be one-tail, and then we'll work with one-tail then. But we got to be cognizant of that. So let's look at the T statistic that we would be calculating. So for the difference of means test that we would run, this is the T statistic. And so as I mentioned before, break it down. It is the measure of difference between the means, the absolute difference between the means, divided by standard error. And that standard error there is to get us in the space so that we can now compare it to a sampling distribution that is standard, has a standard deviation of 1 and a mean of 0. So that's our T statistic. These are the parameters within it. This specifically, and so what we'll do is we'll calculate this T statistic using the difference between the means, using N1, N2, which are just the number of samples that are available to us from each one of those means that were calculated. We got the variance of 1 and 2 from the two different sample sets we're working with. And you notice here, if you look at T critical, when we calculate it, we're going to use our T inverse function. If you're not going to use the two-tail variate, then you're going to take alpha divided by 2. And the degrees of freedom now, it's very interesting. You have two separate data sets you're working with, so you N1 plus N2. But because we're making an estimate about the population mean, we lose two pieces of information because we don't have that for either one of those. And so we're down to N1 plus N2 minus 2. Okay, so we got our T critical, we got our T statistic. This is what we're going to do. If the T statistic is greater than or equal to the T critical, or less than or equal to the positive form of the T critical, it's a symmetric test, we don't care if we're bigger or smaller, then we fail to reject the null hypothesis. Our current hypothesis remains to live to fight another day, and we declare that there's no statistically significant difference in the means. We suspect that these two wells are from the same rock or whatever the problem might be. Now, with that type of test, what we provided is a T critical and a T statistic, and we have a binary outcome. You reject the null hypothesis or you fail to reject it. You may also be interested to know, not just if you reject or what relative to the threshold, you might want to know what cumulative probability value you had. You might find out your cumulative probability value was P 2.2%, which means that you just barely rejected the null hypothesis. That would be kind of interesting to know. Or you might find out that your p-value is in fact 50%. Your cumulative probability was 50%. In other words, you're right in the middle of the distribution. You wouldn't have rejected that for even the most extremely limited confidence level. So those would be kind of interesting to know. You can get the cumulative probability value directly from our T statistic being applied to the standard student T distribution using the degrees of freedom from a table, or you can calculate it. And of course, we know the T inverse function, and here's the form right here. We could look it up. And so at any point, you could, in fact, calculate that specific p-value. And some people actually calculate that p-value and then just use their knowledge about it being a two-tailed test and the confidence level, and they go ahead and decide, oh, if the p-value is between 2.5 percentile and 97.5 percentile, I'm going to fail to reject. And some people do it like that too. So that might be useful to you. Now, the one thing I should mention about this test, it assumes that the variables are Gaussian distributed and the standard deviations are not significantly different from each other. It's known as the pooled variance method. Now, if you look up, you'll find out that some cases you can still use the test. The variables are, close to Gaussian and so forth. And so these are details that we should be careful about. For the purpose of the scope of this course, we will provide and work with examples which meet these metrics so that we're able to run this test. It makes sense. So now you might be in a situation in which you want to work with two distributions which you suspect the variances are unequal. You want to test that the means are the same, but they have different spread, and you know that. And so in that situation, we will use the unequal variances variant of the t-test for difference in means. Its t-statistic still has the measure. The standard error is actually greatly simplified from the pooled variance method that we showed before. And so it's shown right here. And the t-critical value becomes much more complicated. In fact, isn't that funny? There's always conservation of complexity. So our t-statistic, much easier to calculate. But the t-critical, now the degrees of freedom is super complicated. There's a bunch of different factors here, but you'll see that it's all a function of the number of data in both of the data sets and their variances which come into this U parameter here. Once again, you can still get the probability value, the cumulative probability value if you want to further understand what happened with the test. And so after you understand these equations, there is just an element of really plug and chug. It's not too bad after you worked out a couple of examples. So let's go ahead and do that. And we'll do that together. I have it, I'll show it to you in PowerPoint and also pull up the Excel. The Excel will be available to you on Canvas. I'll start putting these on GitHub too so that people can follow along outside of the class. So let's determine whether two data sets come from the same reservoir unit. We're going to compare two data sets of a sample of porosity. We've uploaded it on Canvas. This will be available on GitHub. The name of the file is porosity sample 2 units. Are the means significantly different at a 95% confidence level? So I will give you a chance to work through that, count to 3, and then I'll show the answer. 3, 2, 1. So I did this all in Excel, and I spent a little bit of time on it. And so I plotted the original CDFs of the data sets just so we can compare them to each other. I calculated the means and standard deviations of each one of them, and I have to count the number of data that are available in each case. So I have all of that available right now. Then what I did is I went ahead and I calculated my t-statistic and my t-critical. To do that, I took the measure divided by the standard error. I've broken that up here so you can see the different parts of it. And I calculated the t-statistic directly from that, the t-critical from just taking the inverse of the student t-distribution. If I want to use the two-tail variant, all I have to do is put alpha in, n-1, because we're dealing with the student t-distribution. We don't have the population mean, and so we've got n-1 degrees of freedom. Or if you use the standard t-inverse function, you should actually go ahead and divide alpha by 2 because we want to get it at the lower tail, and we're splitting the alpha between the lower and upper tail. It's a two-tail test. Okay, so that's how we got the t-critical, and then we just do a comparison. Is the t-statistic between the negative and the positive t-critical? It's not, so we reject the null hypothesis. If you want to see what this looks like in Excel, the original data, this was for fun. I created this probability density function right here, just for fun. And actually, it's a discretized PDF. I should say that. It's not actually in density. It's actually in probability. So it's a discretized PDF. I also calculate the CDF. Now, what did I do for this problem? The sample statistics, the mean, and the sample standard deviation, super easy, right? I named those data sets. So X1 and X2 are the fields that have the specific values in it. And so I could do that by shorthand very easily. And I get the count too. So this is the information that I need to move forward. The measure is only going to be the absolute difference between the two means. That's easy. The standard error is going to be more complicated. Of course, we saw that lengthy equation, and this is for the point. This is the case of the pooled variances, so we have kind of a complicated standard error calculation. But you can open up the sheet and confirm, in fact, I put things in the right place. I have all the n's, 1s, and 2s, and standard deviations, and so forth in the right places. Once I do that, I can calculate the t-statistic by just simply dividing the measure by the standard error, and that gets me 3.18. And my t-critical is simply going to be in this case, I have a probability which is going to be equal to, where's G55? G55 is down here. Oh, here it is down here. The alpha level. And I do two-tailed, so I can just put alpha in there at 5%. And my degrees of freedom is number of data in data set number 1 plus number of data in data set number 2 minus 2. And so that's my t-critical. And I do this comparison right here. And I wrote a little if statement that checked it. And it says you reject the null hypothesis. And if you want to evaluate the p-value, how close was I to keeping or failing to reject the null hypothesis? I can go ahead, as I mentioned before, you can actually plug in S43 is that t statistic. You can check where that is within the standard t distribution with the right degrees of freedom right there. So that's n1 minus n2 n1 plus n2 minus 2. And if you do that, you'll find out that p-value was about 0.3%, which means we weren't even close to failing to reject the null hypothesis, because all we needed was 2.5% and we got 0.29%. We're even further out on the tail as far as the cumulative probability goes. So we definitely reject. We would have rejected that at even a 99% confidence level. We would still reject it. Okay, so that's it. That's how you work through that problem right there. Okay, let's go back. I put the summary right here. I'll provide this on GitHub with the specific. I also have a demo, difference in means, on GitHub, which actually provides a really nice formatted sheet for doing this exact type of calculation. Okay. Oh, let's go ahead and try a difference in variances approach. Now you could have gone back and actually, I should show you, you could have gone back and tried to calculate the same problem assuming unequal variances. And if you're interested, I've repeated that with the more complicated degrees of freedom calculation, but with the much more simpler calculation for the t-statistic, right? So I've done that. If you're interested, you can go ahead and you can check and take a look at that. Okay. So let's do an F-test. And so we're going to compare two variances from the two different distributions. We want to see whether or not they're the same, that the variances from the two sample sets could come from the same distribution. In other words, are we suggesting that the variance sampled from the first, the population variance, is the same as the population variance that could have been sampled with the second? And so we're going to compare. Why would we want to do this? Well, variance, as we found out when we talked about heterogeneity, is a very good measure of heterogeneity, variance of permeability. And so that would be important to us to know if the permeabilities are similar. So we could use it for that case. Requirement, the sample and population distributions have to be Gaussian once again to be able to do this. And so let's go ahead. The null hypothesis is that the ratio of variance of data set number 2, or the population number 2, to the population number 1 variance is equal to 1. In other words, they're equal to each other, where we have specifically ordered it so that the population number 2 is assigned to the sample set with the greater variance. That forces us to have a metric or score here that can only go from 1 or greater than 1 by definition. The alternative hypothesis is that they're not equal to each other, that the variance of 2 is in fact greater than the variance of 1. Okay? So what's the F-test? What's the test statistic? The test statistic is simply going to be the sample variance of 2, or A in this case, divided by sample variance of B, once again under the constraint that the sample variance of A is greater than B. So you'll switch them around if it turns out to be that B is greater than A, you'll switch them around. If the F statistic is less than F critical, then we fail to reject the null hypothesis and we state that the two variances are not significantly different from each other. And what does F critical look like? Well, we go to the F distribution. And as we mentioned with the F distribution when we talked about distributions, it has two sets of degrees of freedom along with its significance level. And so the degrees of freedom are going to be the size or number of samples in A -1, the number of samples in B -1, and then we have the significance level. Now we're not doing any of that dividing by 2 stuff because of the fact that we are dealing with a problem that is by design one-tailed. You can see that because the fact that we set the variance of A has to be greater than the variance of B, and the result of this statistic can only be 1 or greater than 1. And so we want to reject. If we get out too far, the ratio becomes too large, we go too far out on the tail. Okay, so now we should note too that for this specific test that assumes the two variables are Gaussian distributed, but it's been found that if you're working at an alpha level of 5% or a confidence level of 95% with a similar number of samples, that this method is still robust if the data are not Gaussian distributed. So we'll use this in general. We'll be fine using this in many of our situations that we go through. Okay, well, how do we get the F value, the F critical value? Well, we're going to go to a table and we can look it up. And so the table will have the degrees of freedom of the denominator, the variance that's less than the other variance, and of the numerator, the one that's greater. And so we'll find our F statistic directly from that. We can also use Excel with an F inverse function to look it up precisely. Okay, so let's try another example together. And so are the variances different between well 1 and well 2. And so if in this example, what I say is that well 1 variance is 4% squared, so the standard deviation would be 2. And well 2 variance is 9% squared, so the standard deviation would be 9. And they each have 25 samples. So the F statistic is going to be, the F statistic will be 2.25, which is going to be the variance of the larger divided by the variance of the smaller one. And now we want to test to see if we are less than or equal to, with our F statistic, than the F critical. And if we are, then we fail to reject. And so what's the F critical? We have the number of data. For the one with the larger data set, where I want to make sure I got that right. Yeah, the one with the larger data set first, which is the one with the greater variance, we go with 25 minus 1. Those are going to, that will be our degrees of freedom. 20 minus 1 for degrees of freedom for the one with the smaller variance. And we put in the significance level of 5%. Once again, no worrying about having to divide by 2 since it's a one-tailed test. And we get 2.11. And so what do we say about that? Well, we say that in this case, we have an F critical value that is less than the F statistic. So we reject the null hypothesis. The variances are significantly different. To get the F critical, once again, this is the equation that you would use within Excel. By doing right tail, this is interesting. It just switches around the distribution. So you can put in a 5% and it will give you the cumulative probability of 95%, the right tail. If you don't do the right tail, then you have to take 1 minus alpha because you want the 95th percentile to get that upper bound on the right-hand side of the F distribution. So that's how either one of these would give you the same answer within Excel. So let me give you another problem. Determine if 2 data sets come from the same reservoir unit. You've already tested the difference of means. Now you want to test the difference in variances. Use the same data set we used for that previous problem. Are the variances significantly different at a 95% confidence level? So go ahead, take a try at that. I'll go ahead and pull up the answer and show it to you in 3, 2, 1. Okay, so this is what it looks like if we go ahead and just walk through it. Once again, we're going to do the F test for difference in the variance. We take our data sets, we calculate the mean, we have the variance, we have the count. We did that before. It's good to have those summary statistics. Our F statistic is simply going to be take the one that's larger and divide the one by the one that's smaller. That's our F statistic. Our F critical will come from the alpha value, which is 5%, comma, we'll take the number of data in the first one, minus 1 for the first degree of freedom, and for the second data set that we worked with, minus 1. The main thing is just keep everything consistent between your A and your B, and you're fine. So when we do that, the result is we get an F statistic of 2.67, we get an F critical of 2.17. So our F critical is greater than our F statistic is greater than our F critical, so we reject the null hypothesis. Now you could also calculate the probability, the p-value, the cumulative probability of that value. And that can be pretty useful. That comes from right here, where what we did is we just said, look up from the F distribution, right-tailed, the specific value we got for an F statistic with the right degrees of freedom, and that gives us the p-value, the cumulative probability of that outcome, and it's 1.9%. So we can see that we're well below the 5%. We're well below the 5% that we assigned for our alpha, and so it tells us that in fact we would have definitely rejected that. We're not even close to keeping the null hypothesis or failing to reject the null hypothesis. So that can be very instructive for us. Okay, So that's the example of an F-test. That example will be available on GitHub. Here's a summary. Here's a summary of the commands you need in Excel in order to solve this problem. Let's talk about the chi-square distribution to finish off our talk about hypothesis testing. Chi-square distribution, what you can do is you can compare two distributions. The example is that we assume we have data set that consists of 100 chemical measurements from a sandstone unit. We could use the chi-square test to test if these measurements can be described by Gaussian distribution. That's pretty useful. So we fit a Gaussian distribution to the sample data and variance, and then we compare the two distributions, the original distribution against the one that we fit. How would we fit? Well, that's pretty easy. You calculate the mean and the standard deviation. You now have a complete distribution, and now we're just comparing our data-derived distribution, non-parametric distribution, to a parametric distribution. It permits us to test if two distributions were derived from the same distribution from the same population potentially. Independent of the distribution that's being used, there's no assumption about that. Null hypothesis, two distributions are the same. Alternative hypothesis, the two distributions are different from each other. What's the test setup look like? Well, what we do with the chi-square test is we have n data, and they're grouped into k classes. The k classes are just k bins. They're equally spaced bins along the data values. And so we're dealing with total organic carbon here. And so we would have bins that maybe look like they're on the order of maybe 0.5% or so. So what we do then is our chi-squared statistic is going to be taking a summation of the square difference between the observed frequency and the expected frequency. And we are squaring that, of course, and we're standardizing by the expected frequency. That gives us our chi-square statistic. So we would be comparing our observed data versus the fit Gaussian distribution. That's how we would set that up. And we get our chi-square statistic. Now, the chi-square critical value will depend on the degrees of freedom, which we calculate here as being the number of classes minus the number of parameters that were plus 1. So in the case of Gaussian distribution, we have two parameters, a mean and a standard deviation, and we add 1, so we would have a z value equal to 3. So we would use, for degrees of freedom, number of bins minus the 3, which would be our z value there. So we could go ahead. Notice from this calculation here, we're taking a square and a sum of a square. So this is going to be a one-tailed test. So we're going to be concerned about our alpha being out on the right tail, or the area that we're rejecting under the curve being out on the right tail only. A very large value would indicate a very large difference between the two distributions, where a very small value would indicate that the distribution is very similar. So we want to reject when we have a very large value out on the right tail. So we will use as our critical chi-square value a percentile value of 1 minus alpha. So it could be 95 percentile is what we want to look up with those degrees of freedom. So I've worked out an example of using the chi-square test to test for the difference between two distributions, and it's available to you in the QQplot chi-square demo.excel, and it has some additional functionalities such as plotting the bin probability density functions and the QQplot and so forth. It has the chi-square test where we take the data ranges, we bin them into multiple bins, we look at their relative counts within each one of those bins to calculate the chi-square statistic, we calculate the chi-square critical, and from that we're able to determine that we fail to reject. In fact, the chi-square statistic turns out to be 6.3, the chi-square critical is 12.6, so soundly we have failed to reject, and we retain the null hypothesis that the two distributions are the same as each other. So with that, that brings us to the conclusion of our discussion about hypothesis testing. That also finishes up all of the discussions around univariate statistics, and it frees us up to get into, or prepares us at least, to be able to get into discussions around bivariate statistics, which are next. We'll get into more spatial analysis, machine learning, uncertainty analysis, and so forth as we go along. And so this has really been a lot of the groundwork that was required for us to move into what I think are more interesting statistical approaches, but at the same time, I don't diminish it that there are many opportunities to use what we have discussed in order to have business impact, no matter what you're doing, trying to quantify, look at distributions, trying to look at probabilities, trying to look at confidence intervals, and so forth. They all have really great utility within your professional career. I'm always happy to discuss further. I'll see you next time in Bivariate Statistics.